In medieval Europe, the first mechanical clocks were so inaccurate they could lose hours in a single day. Yet towns still built towering clock faces to display them proudly. Why? Because even flawed time was better than no time at all. In this video, we'll take a quick tour through the strange and clever ways ancient people measured time, and the few breakthroughs that forced entire societies to rebuild how they worked, worshipped, and traveled. It all began long before gears and bells, with nothing more than sunlight casting shadows across the ground. Imagine standing in the middle of an ancient city square, the ground beneath you marked with lines, and a single post casting its shadow slowly across them. This was humanity's first real clock, the sun's shadow. It was simple, silent, and for the first time, it gave shape to the passing hours. The earliest surviving example archaeologists have dated comes from Egypt around 1200 BC, discovered in the Valley of the Kings. It wasn't a fancy carved stone dial, but a modest, T-shaped shadow clock. A bar on the ground cast a shadow that crept across divisions, scratched into the earth or onto stone. Those divisions turned daytime into measured slices, and suddenly people had something astonishing, hours they could point to. There was, of course, a catch. Days weren't consistent in length. In summer, shadows stretched differently than in winter, so 1 hour in July might last much longer than 1 in December. Ancient Egyptians accepted these seasonal hours, dividing daylight into 12 parts regardless of how long each actually lasted. Nights were also mapped into 12 divisions, marked out not by shadows, but by the rising of certain stars known as decans. Later cultures, especially in the Greek and Hellenistic world, refined these ideas and moved toward dividing time into 24 equal hours, allowing people to imagine time as a constant, rather than something that stretched and shrank with the seasons. As centuries passed, sundials became more sophisticated. The Greeks and Romans engineered hemispherical dials, like a bowl carved with hour lines, designed to compensate for the shifting path of the sun in the sky. These bowl-like designs brought a little more regularity. They didn't erase the inequality of seasonal hours, but they made daily life more predictable. For a farmer, that meant knowing when to start or stop tending the fields. For priests, it meant ceremonies could take place at precisely the right moment, not simply when the sun felt high enough. Sundials weren't just tools. They became landmarks. Large stone dials decorated temple courtyards, royal gardens, and bustling marketplaces. Some were monumental in scale, built by the Persians or mounted in Roman forums where entire communities could see the hour together. This made time public and shared, no longer just a private guess based on the sky. But even the grandest sundial still had an obvious weakness. It disappeared on cloudy days. For a society growing dependent on schedules, this problem was more than a nuisance. Without shadows, when was the market supposed to open? When should workers expect their wages? What makes sundials so remarkable isn't only that they measured time, it's that they reshaped how people thought about it. Before sundials, a day was loosely framed by chores or natural cycles. Sunrise meant waking. Dusk meant resting. After sundials, life began to take on the rhythm of hours. Temples started rituals at fixed times. Public announcements occurred on schedule. Even labor shifted, with wages discussed not in days alone but by the hour. For the first time, time itself became a ruler against which human life was measured. Yet despite their influence, sundials could only serve when the sun was kind enough to shine. Nightfall or storms made them useless. And that raises an intriguing question. If sundials were so widespread and practical, why would anyone go to the trouble of inventing noisy, complex, mechanical clocks? Or put more simply, when daylight failed, how did people keep track of time? At night, the sky itself became a clock. Around 600 BC, Egyptian astronomers turned to a tool called the merket to read the hours in the darkness. It looked unimpressive, just a straight bar with a plumb line hanging down. But when used in pairs, it became a precision instrument. One merket lined up with a fixed star near the pole, while the other measured the crossing of other stars. As these stars shifted across pre-marked points in the sky, the Egyptians could divide the night into 12 hours, mirroring the structure of their daytime system. To make this possible, they memorized the rising patterns of 36 specific stars, known as decans. Each decan rose at different times of year just before dawn, creating a rotating cycle that also served as a calendar. As one star disappeared with sunrise, another would take its place, and this pattern repeated roughly every 10 days. By tracking these 36 decans, priests could both tell the hour and anchor the seasons, keeping festivals and rituals on schedule. Still, the system had limits. The merkets required clear skies, and on cloudy nights, the stars vanished. To cover those gaps, Egyptians turned to a second invention, the water clock. A simple pot with a tiny hole allowed water to drip out at a steady pace, and markings inside the vessel measured time as the level fell. These clepsydras were less reliable than star tracking. They sped up or slowed down, depending on the temperature, but they gave a usable backup when the heavens were obscured. In effect, Egyptians developed a two-part system: star clocks when the sky was visible, water clocks when it was not. This pairing was more than clever. It gave society a way to live by time, even in darkness. In temples, priests used it to begin ceremonies at exact hours of the night. Farmers could prepare for planting by watching the stars shift with the seasons. Even the Nile's crucial flood cycle tied back to knowing not just the day, but the hour. Where sundials had first imposed order on daylight, merkets and water clocks did the same for the night, ensuring time never ceased to flow. Later, other cultures refined these ideas. By around 300 BC, the Greeks built more advanced water clocks that added floating indicators to mark the hours on a visible scale, much like an early clock face. But the principle stayed the same. Astronomy offered the true reference, while steady mechanics kept the count when nature's signals went missing. This combination reshaped everyday life. Guards could change shifts according to a schedule rather than guesswork. Travelers knew how long was left until dawn. Rituals followed a fixed rhythm, no matter the season. With tools as simple as a plumb line or a dripping jar, the night was no longer an unmarked stretch between sunsets. It became predictable, structured, dependable. Yet even with hours mapped across both day and night, another challenge remained. People still needed to predict not just the passing of hours, but the turning of seasons, deciding when to sow crops, when festivals should fall, and when floods would return. Keeping track of days and years required more than shadows or stars. Ancient societies needed a way to anchor life's big events, when to crown kings, celebrate festivals, or prepare fields for planting. This led to one of humanity's most important inventions, the calendar, a system designed to braid together the rhythms of the moon and the sun. The challenge was that these two cycles never quite aligned. A lunar month, marked from one new moon to the next, averaged about 29.5 days. A solar year, the time it takes Earth to orbit the sun, lasted roughly 365.25 days. The mismatch created a puzzle. If you relied only on the moon, the months slipped out of sync with the seasons. If you relied only on the sun, the moon's phases were ignored. Different cultures proposed different solutions. In Egypt, around 3000 BC, officials introduced a civil calendar that cut the lunar cycle out altogether. Instead, they divided the year into 12 months of 30 days each, and then added 5 extra festival days at the end of the year. These were called epagomenal days and were treated almost like time outside the year itself. The structure was elegant, but without leap years it drifted slowly, about 1 day every 4 years compared to the solar year. Over the span of 1,160 years, however, this steady drift completed a full cycle, eventually realigning with the agricultural seasons. Mesopotamian societies solved the problem differently, preserving the moon's importance. Their earliest lunar calendars slipped quickly out of step with harvest seasons, so priests had to occasionally insert an extra month. Over time, Babylonian astronomers developed a sophisticated system, a 19-year cycle, similar to what we now call the Metonic cycle, with 7 intercalary months spread throughout. This kept lunar months tied more accurately to solar years and seasonal cycles. Their refinements spread widely, influencing Hebrew, Greek, and later calendars across the Mediterranean. On the other side of the world, the Maya achieved something even more ambitious. They didn't just use one calendar, they used several, layered together. The 260-day Tzolkin structured religious life, tracking sacred rituals and divination. Alongside it, the 365-day Harb acted as a solar year. When the two cycles overlapped, every 52 years, it marked a calendar round, a moment of renewal. They also maintained a long count calendar, which stretched back to a mythic creation date and mapped history on a grand scale. This interplay of cycles turned time into something multidimensional, simultaneously religious, agricultural, and historical. Other cultures experimented with their own blends. The Greeks built upon Babylonian insights with their own 19-year Metonic cycle. Though accurate, many city-states preferred their local systems, keeping time fragmented across regions. Early Rome's calendar was especially irregular, originally counting only 10 months with an unmarked winter gap. Political leaders even manipulated the addition of months to extend or shorten their terms in power, creating chaos. Stability returned in 45 BC, when Julius Caesar, with help from Egyptian astronomers, introduced the Julian calendar. It followed the solar model, dividing the year into 365 days and adding a leap year every 4. Compared to earlier experiments, it was far more stable. The Julian system endured for over 1,600 years, though it still drifted slightly, by about 11 minutes per year, requiring later refinements that eventually led to the Gregorian calendar many of us use today. Calendars transformed daily life in ways just as profound as hours or minutes ever did. They coordinated religious rituals, guided farming cycles, and provided traders with predictable market seasons. More than a record of days, they offered a shared framework so entire cultures could move in step with one another. But while calendars solved the riddle of years and seasons, they left another problem open. People still needed a way to measure much shorter spans, not when spring would return, but when a guard's watch should end, or a speech should begin. Solving that puzzle called for a very different kind of device. Water itself became one of the earliest ways to keep time. Around 1600 BC, the Egyptians and Mesopotamians used simple devices called clepsydrai, or water clocks. These were nothing more than clay pots with small holes. As water dripped steadily out, lines marked on the inside recorded the passage of hours. It was practical, but not perfect. Temperature and pressure affected the flow, sometimes slowing it, sometimes speeding it up. Seasonal adjustments were often needed, but still, the system worked when sundials failed. Greek engineers refined the idea centuries later, around 325 BC. They introduced regulating tanks that kept the water pressure consistent, allowing far more accurate measurements. Some versions even featured floating indicators that rose or fell inside the vessel, sliding past a scale like an early clock face. In courtrooms at Athens, water clocks timed speeches, ensuring orators had equal speaking hours regardless of status. More advanced Greek designs added gears and dials, turning the steady drip into displays of cosmic motion that could track not only hours, but also the movements of the planets. In China, water clock technology reached a scale unseen anywhere else. The most impressive example appeared in 1088, when the scholar and engineer Su Song built an enormous clock tower more than 30 feet high. His design used scoops, gears, and counterweights, powered by falling water, to drive a rotating celestial globe and an armillary sphere, an instrument showing the positions of stars. Mechanical figures inside the tower rang bells, struck drums, and even moved in sequence to mark the hours. The whole system achieved extraordinary consistency, losing less than 15 minutes in a day. For its time, it was closer to a scientific observatory than a simple clock. The utility of water clocks stretched across cultures. Temples used them to mark the start of nighttime rituals with dependable regularity. Astronomers relied on them when charting the heavens, since paired with careful observation, they allowed more precise records of celestial events. In city squares and palaces, they provided a reliable benchmark for daily life, free from dependence on clear skies or direct sunlight. Across the Persian courts, Byzantine monasteries, and even Mesoamerican ceremonies, the same principle appeared. Time could be captured by the steady, predictable flow of water under gravity. These devices weren't just tools, they sparked discoveries. The Greek engineer Ctesibius noticed that water flows more evenly when pressure is carefully regulated. Insights that became the foundation of hydrostatics. Centuries later, in the medieval Islamic world, scholars improved water clock systems further with geared mechanisms. Some were ornate creations that chimed on the hour, a step closer to the mechanical clocks that would eventually dominate Europe. Yet for all their ingenuity, water clocks had their drawbacks. They required maintenance, frequent refilling, and careful cleaning to prevent mineral buildup. Large versions were impressive but bulky, and their operation demanded expertise that made them less practical outside temples or royal observatories. While they remained useful for centuries, they also highlighted the need for portable, less labor-intensive ways to track time. The real breakthrough of water clocks was less about convenience and more about thinking. By converting a natural, continuous flow into measured units, they proved that time itself could be mechanized. That mental leap of linking steady motion to measurable hours directly prepared the ground for the gear-driven mechanical clocks that would soon follow. But not all timekeepers relied on flowing water. In some places, the answer was far more dramatic. They measured the hours with fire and smoke. Sometimes the simplest idea was also the most brilliant. Measuring time by watching something slowly burn away. Indoors, where sundials gave no help, and water clocks were impractical, people turned to candles and incense. By marking them carefully and letting fire do the work, entire societies kept hours with flame and smoke. China led the way with some of the most creative designs. By around 520 AD, incense clocks appeared in temples and imperial courts. These weren't just sticks of fragrant smoke, but carefully crafted devices, coils or powdered trails laid out in grooves that burned along measured paths. Each segment represented a fixed interval of time, and different blends of incense added meaning. A sweet perfume might signal 1 hour, while a heavier smoke marked the next. Some even had small metal pins inserted at intervals that dropped onto gongs as the line burned, creating an audible signal in the middle of the night. These clocks were practical and ceremonial at once, a way to measure time in darkness, while also filling halls with scent during rituals. Europe took a parallel approach, relying on candles instead of incense. In monasteries and castles, candles marked with lines at regular intervals became indoor hour markers. As the wax melted past each mark, another hour was gone. A medieval legend even credits King Alfred the Great of England with using candle clocks to divide his day for prayer, work, and rest. Whether that story is true or not, the broader idea was already widespread. Measuring time not by gears or stars, but by watching a candle shorten. Like all clever inventions, these burning clocks had limits. A draft could make a candle's flame leap and eat wax unevenly. Humidity might slow or quicken incense trails. Cheaper tallow candles dripped and smoked, while beeswax burned steadily but came at a price most ordinary people couldn't afford. Some designs tried to balance out these flaws. Metal shields blocked the breeze, and weighted strings hidden inside candles dropped as they melted, striking bells to signal the passing of an hour. Portable versions existed too. Folding candle clocks carried by travelers or small lantern-style clocks that became useful in workshops and marketplaces. What makes these devices fascinating isn't just their function, but their imagination. Burning materials were everyday objects: wax, incense, tallow. Yet people transformed them into precise tools. A candle clock in a cold, windowless monastery let monks rise for midnight prayers. A coil of incense in a Japanese tea house set the pace for an exact ritual. The kodoki tradition in Japan, which used powdered incense measured into carefully laid lines, demonstrates how scent and time could merge into a multi-sensory experience. These aren't just clocks, they're reminders of the creativity of pre-mechanical societies, where even smoke served as a ruler of the hours. Though mechanical clocks eventually took over, candles and incense never disappeared completely. In villages far from expensive metal gears, marked candles continued to measure family routines well into the 18th century. In temples, incense clocks survived as both practical and symbolic tools. Even modern technologies echo the same idea. In mines, slow-burning fuses once regulated shifts, and in some specialized cases today, time is still measured by controlled burning. These humble timekeepers demonstrated that accuracy wasn't always the goal. Dependability in context was. A sundial froze under clouds. A water clock might clog with ice. But a candle or coil of incense burned steadily in a sheltered room. By giving people a reliable indoor option, they bridged the gap between nature's cycles and human schedules. And that search for precision soon inspired even more ambitious tools, ones designed not just to tell the hour, but to chart the very movements of the stars. How did ancient scholars track the heavens without telescopes or modern tools? they relied on astrolabes, ingenious brass instruments often described as the smartphones of their world. Compact devices that combined astronomy, mathematics, and practical timekeeping in the palm of your hand. An astrolabe looked like a disc covered in intricate engravings, with rotating parts that mirrored the movements of the sky. At its simplest, it projected the curved heavens onto a flat plate. The main body, called the mater, contained engraved scales, interchangeable plates, or tympans, adjusted for different latitudes. On top, a star map called the rete spun like a cut-out web, its pointers marking bright stars. By aligning these pieces with the sun or a specific star, a user could calculate the hour of the day, determine which constellations should be visible, or even predict when dawn would break. Islamic astronomers pushed this design to remarkable heights during the Golden Age. By the 9th century in Baghdad, refined astrolabes appeared in mosques to set precise prayer times, taking into account the sun's changing path across the sky. Travelers carried models with interchangeable plates, so the device worked accurately anywhere from North Africa to Central Asia. Manuals explained hundreds of uses, from predicting lunar phases to calculating the Qibla, the direction of Mecca. Abd al-Rahman al-Sufi, for instance, filled hundreds of pages with explanations of practical applications. Later examples became even more advanced. In 1221, in Isfahan, Al-Farisi produced a geared astrolabe that combined rotating components for stellar calculations with impressive accuracy, showing just how far the instrument could go beyond its Greek prototype. The precision was striking. In skilled hands, an astrolabe could measure time within about 15 minutes, a level of accuracy that outperformed many medieval mechanical clocks. Unlike sundials that struggled with seasonal changes, the astrolabe allowed conversion between unequal seasonal hours and the equal hours that eventually became standard. This meant religious rituals, daily work, and study could all be coordinated around predictable celestial patterns, not just shifting shadows. Their value extended beyond the observatory. Simplified mariners' astrolabes gave sailors tools to measure the sun's height at noon and calculate latitude during long voyages. These versions were heavier, cut from thick brass with open-work designs to resist winds at sea. Portuguese navigators carried them during the Age of Discovery, and records show Christopher Columbus brought one aboard, though his lack of training meant he misused it. Even so, the instrument was vital to explorers mapping new routes across the globe. Astrolabes could also be symbols of sophistication. Wealthy patrons ordered elaborate versions inlaid with silver detailing, ornate inscriptions, and finely carved geometric art. They sometimes carried not just star maps but calendar scales, zodiac markers, or conversion tables. Owning one announced both wealth and learning. After all, using it required a grounding in mathematics, astronomy, and geometry. By the 14th century, universities in Europe taught the astrolabe as a core instrument. It arrived through Islamic Spain and spread into scholarly circles, where it shaped teaching for generations. Even Geoffrey Chaucer, famous for his poetry, wrote a guide explaining the device's workings for his own son. But after the 17th century, astrolabes gradually gave way to telescopes and new mechanical clocks that offered more specialized precision. What makes them even more fascinating is how close they came to early computing. The reed and rotating plates worked like a mechanical algorithm. Turn the discs, align a star, and the device calculated spatial and temporal relationships instantly, long before calculators or apps. Astrolabes embodied the power of analog problem solving. They were bridges between the heavens and the human world, linking astronomy with navigation, faith with daily routine, and science with artistry. Yet for all their genius, they were also fragile, costly, and confined to trained elites. Which raises an intriguing question. If astrolabes could do so much, why did they eventually fade from everyday use? The answer lies in a completely different kind of timekeeper, one so simple and rugged that it could survive life at sea. At sea, accuracy meant survival, and one of the simplest tools proved most dependable: the hourglass. While astrolabes needed clear skies and pendulum clocks swung uselessly with the waves, the steady fall of sand kept ticking regardless of storms or calm. Hourglasses became the sailor's standard, their reliability born of both design and practicality. On Ferdinand Magellan's first circumnavigation in 1519, his ships carried 18 hourglasses. The job of flipping them every 30 minutes belonged to the ship's boy, and each turn was marked by the ringing of a bell. This rhythm created the watch system at sea, dividing work shifts into neat intervals, a system still reflected in nautical timekeeping today. The sound of the bell and the sight of falling sand structured life aboard, guiding meals, rest, and changing duties. Several features made hourglasses especially suited to maritime use. Their sealed design protected the contents, and sailors mounted them in sturdy wooden frames to keep them steady when waves rolled the deck. Finely ground materials, often marble dust, powdered eggshell, or carefully sifted sand, were chosen because they flowed smoothly without clumps. These refinements reduced the effects of humidity and shipboard moisture, though they never eliminated the natural wear that came with daily use. Limitations were unavoidable. Hourglasses could only measure short spans, usually half an hour or an hour, meaning constant resetting. The narrow waist that allowed sand to trickle through also wore down over time, changing the rate of flow. Crews coped by keeping several glasses running at once, comparing them to catch errors, and recalibrating against the noonday sun whenever weather permitted. Some vessels carried larger 4-hour glasses for nighttime watches, but their accuracy tended to drift the longer they ran. Designs improved as maritime needs grew. Early versions might be made from clay or wood, but by the 14th century Venetian glassmakers produced finely crafted, reliable glass models. To protect them, sailors packed hourglasses in wool-lined cases so they could survive rough handling. Some ships even carried 3-bulb models or kept multiple spares, because a single accident could mean the loss of the crew's only measure of time. Their utility stretched far beyond intervals. For centuries before precise marine chronometers, longitude was impossible to calculate without accurate time. By measuring distance traveled between daily sun sightings, sailors relied on hourglasses to piece together their approximate location. Even a small error, say a glass drifting by several minutes each day, could translate to navigational mistakes spanning hundreds of miles. Until the 18th century, the hourglass remained the best available solution for seafaring timekeeping. Though primarily practical, the hourglass also seeped into culture and symbolism. In artwork, it often appeared beside skulls in memento mori paintings, a reminder of life's brevity. Monarchs placed them on tables during negotiations to limit discussion time, while churches sometimes used them to time sermons. These symbolic meanings added layers of significance to what was, at its core, a utilitarian tool. By the 18th century, advances in spring-driven chronometers gradually displaced the hourglass for navigation, but its influence persisted. hourglasses lingered in homes, classrooms, and workshops as everyday timers. Their familiar shape became shorthand for the idea of passing time, appearing in everything from board games to digital loading icons. More subtly, the half-hour intervals of the ship's bell system, still in use today, trace directly back to those grains of sand flipped by generations of sailors. Hourglasses had proven that even the simplest devices could shape entire ways of life, structuring work, movement, and routine. But while ships kept time in half-hour beats, back on land a transformation was underway. Whole communities were about to order their days around a single shared clock. What happened when time stopped being private and became something everyone could hear at once? In medieval Europe, the answer arrived in the form of public clocks, towering machines that chimed across towns and dictated the rhythm of daily life. These new devices didn't just track hours, they transformed how entire communities understood and obeyed time. The first widely recorded example came in 1283 at Dunstable Priory in England. This was no sundial or dripping jar. Instead, it was a mechanical system of weights and gears that automatically struck a bell at regular intervals. No one needed to flip an hourglass or tend a water clock. The sound of the bell was enough, calling monks to prayer without constant reference to the sun. By the early 1300s, similar clocks appeared in cities like Milan and Strasbourg, public symbols of both faith and civic pride. Of course, these early machines were often wildly imprecise, sometimes drifting by many minutes, even hours, over the course of a day. Their verge and foliot mechanisms, little more than swinging bars regulating gears, had a habit of speeding up or slowing down with every change in temperature or with the wear of wooden parts. Towns often reset them daily using sundials when the sun was visible. But the absolute accuracy mattered less than the fact that everyone heard the same chime at the same moment. That consistency, even if imperfect, created a shared rhythm unlike anything people had experienced before. This mechanical beat reshaped life in medieval towns. For most citizens, the practical use wasn't reading dials. Many clocks didn't even have them, but listening for bells. Work shifts began when the bell struck. Markets opened and closed on cue. Curfews kept the streets quiet after a certain hour. Suddenly, peasants who had once worked by daylight and season found themselves negotiating with time enforced by a tower. This was a cultural jolt. Time was no longer tied only to nature, but was imposed from above, ringing through stone walls and across crowded squares. At first, not everyone welcomed the change. Many workers resented clocks that replaced task-based labor with strict hourly schedules. Before, you worked until the job was done. Now, bells told you exactly when to start and stop. This shift laid the groundwork for wages calculated by the hour instead of the day. Some resisted the loss of flexibility, grumbling at bells that demanded punctuality. Would you have welcomed a town bell telling you when to work, or would you have resented it? Tell us in the comments below. Clock towers carried political as well as religious weight. Churches used them to organize prayer, while city rulers recognized their value for administration. A grand public clock was a show of power, a way of declaring that order ruled here. Some models turned into wonders of engineering and spectacle. Strasbourg's clock, for instance, had moving figures and even a mechanical rooster that flapped its wings and crowed at noon. Town councils often fined clock keepers if their charges ran off time, proving how seriously communities now treated this shared standard. By 1500, Venice alone had 17 public clocks, each syncing neighborhoods to the same official rhythm. Keeping these machines alive was no small job. Clock keepers climbed towers daily to rewind heavy weights, apply grease, and adjust worn teeth on wooden gears. Towns often paid them well, or gave them privileges like tax exemptions. Building these clocks was costly, sometimes rivaling the expense of small churches, yet communities invested anyway. Their existence wasn't just about marking time. They embodied identity, unity, and local pride. Still, the transition unfolded unevenly. Sundials and hourglasses continued in rural areas for centuries, and farmers lived by the seasons rather than tower bells. But cities felt the difference most sharply. There, public clocks created something new, a collective schedule, one where individuals had less say in their own pace. The challenge remained, though. Consistency was useful, but true precision was another story. The early escapements that powered these clocks left much to chance. A swing too fast one day, too slow the next. The quest for a steadier heartbeat in these mechanisms was just beginning, and inventors were about to introduce the first great solution. Medieval clockmakers, their machines would run frustration, but never at a steady pace. Their machines would run. The breakthrough that finally gave mechanical clocks their first heartbeat. The breakthroughs that finally gave mechanical clocks their first introduced around the verge and foliot escapement. This was the earliest system that regulated gear movement in steps. This was the earliest system that regulated gear movement in steps, giving clocks rhythm rather than a constant rush. Giving the design itself was clever, chaos, but not overly complicated. The design itself was clever, a vertical rod called the verge carried two angled pallets. A vertical rod called the verge, crown-shaped carried two angled pallets. Attached to the rod was a crossbar, the crown-shaped foliot. Attached to the rod at either crossbar. The foliot. As the foliot rocked with small weights at either end, it twisted the verge. As the foliot releasing one tooth of the gear at a time, the verge. Releasing one tooth of the gear at a time. Just a step. Each turning continuous force into controlled motion. Turning continuous force into controlled time could now be measured in regular beats. This meant even if those beats weren't in regular uniform. Even if those beats weren't perfectly uniform, was a relative term. Still, a foliot swing depended heavily on factors like friction. A foliot swing depended heavily on factors like friction. Where clockkeepers quickly learned that a slight nudge inward or outward, clockkeepers quickly learned that a slight or slow down dramatically could make the foliot speed up or slow down dramatically. Early tower clocks could vary by many minutes without constant tuning, or even hours. Early tower clocks could vary by many minutes, or even seasonal changes made things worse of a single day. Winter cold, seasonal changes made things worse. The foliot. Winter cold, summer heat did the opposite and slowed the foliot. Accuracy shifted constantly, while summer heat did the opposite. But compared to sundials or water clocks, constantly. These machines were still sundials or water clocks. Some of Europe's earliest surviving tower clocks demonstrated just how earliest surviving tower clocks was. Demonstrated just how transformative this was. Installed in 1386 and still running today. Installed in 1386 and still running today to strike its massive bells. Used the verge and foliot escapement to strike its massive bells. Each beat marking about 1.25 seconds. Each beat, although this didn't guarantee precise hours, seconds. The clock created for the first time a steady mechanical pulse. The clock created for the first time a steady mechanical pulse. Loud enough monasteries, city councils to order their lives, and marketplaces, monasteries, city councils, and marketplaces all began to rely on this rhythm. A machine now set the schedule, and instead of the shifting sun, a machine now set the growing presence of these clocks gradually reshaped how time was experienced. The growing presence of these clocks by the 14th century shaped how time was experienced. Single-hour hands began to appear by the 14th century in civic towers. Clock dials with single-hour hands began to appear on cathedrals and civic towers. Later, some German clockmakers experimented with minute hands. Later, some German clockmakers experimented with minute hands. Though true
what mattered
usefulness
most
would only
at
come
this stage
centuries later
wasn't
with
precision,
pendulum clocks, but consistency.
What mattered most at this
Hearing
stage wasn't
seeing
precision,
a shared measure
but
of
consistency.
time. Nudge society away
Hearing
from
or seeing a
task-based
shared
rhythms
measure of
toward
time.
fixed schedules.
Nudge society away from
Maintaining these
task-based
machines
rhythms
quickly became a
toward
specialized
fixed
occupation. Clock
Maintaining
keepers had
these
to oil
machines
gears
quickly
with animal
became a
fat,
specialized
shift
occupation.
foliot weights as the
Clock
seasons
keepers
changed,
had to oil gears
and
with
reset
animal
dials
fat
by comparing them
shift
to the sun
foliot
at noon.
weights
As the seasons
Large
changed,
cities often
and
hired
reset
full-time
dials
wardens
by comparing them
sometimes
to the sun
paying
at
them
noon.
not only with wages.
Large
Also
cities
housing
often
and
hired
supplies.
full-time wardens,
And in several towns,
sometimes paying them not
elaborate
only with
astronomical
wages,
clocks
but
went
also
beyond
housing
timekeeping,
and supplies, displaying calendars,
and in several towns,
zodiac signs,
elaborate
and even
astronomical
animated
clocks
figures
went beyond timekeeping.
Prague's famous
Displaying
1410
calendars,
horloge, for
zodiac
example,
signs,
and even
required constant
animated
attention.
figures. Prague's famous
Despite the
1410
trouble,
horloge, the verge
for example,
and foliot system
required
endured for more
constant
than 3
attention.
centuries. Despite the
It
trouble,
was durable,
the
simple
verge
to
and
repair,
foliot system
and
endured for
effective
more than
enough
3
that many
centuries.
medieval towers kept
It was
using
durable,
variations of
simple
it
to
long
repair,
after more
and
advanced
effective enough
mechanisms
that
appeared.
many medieval towers kept
Even today,
using variations
restored
of it
turret
long
clocks
after more
sometimes run
advanced
on their
mechanisms
original
appeared. Foliot-driven escapements. Even today, their slow rocking
restored
bars
turret
visible
clocks
inside
sometimes
museum
run
cases.
on their original
But the
foliot-driven
flaws were
escapements.
obvious.
Even
Their
to
slow
those who
rocking
maintain
bars
them visible inside
A
museum
clock
cases.
that might run fast one week and
But
slow
the
the
flaws
next
were obvious.
couldn't meet the
Even
growing
to those who
appetite
maintain
for precision. A clock that
The
might
verge
run
and
fast
foliot
one week and slow
was a
the
brilliant
next
first attempt at
couldn't meet the
regulation.
growing appetite for
But its
precision.
inconsistency,
The
highlighted
verge and
the
foliot
need
for something
was a
better.
brilliant first attempt at
Something
regulation.
based not on shifting
But
weights,
its inconsistency
predictable,
highlighted the
natural
need
motion.
for something better.
The
Something
foliot
based
allowed
not on
clocks
shifting
to function
weights,
reliably
but on
for the
a
first
predictable,
time.
natural
Yet
motion.
it also set the
The
stage
foliot
for the true
allowed
leap
clocks to
forward,
function
the
reliably
pendulum.
for the first time.
When Christian Huygens
Yet it
introduced
also
the
set
pendulum
the stage
clock
for
in
the true leap
1656,
the pendulum.
he gave timekeeping a level
When
of
Christian
accuracy
Huygens introduced
that
the
earlier
pendulum
machines
clock
could
in
never achieve.
1656. For
He
centuries,
gave timekeeping
mechanical
a level
clocks
of
drifted
accuracy
wildly,
that earlier
often
machines
losing
could
or
never
gaining
achieve.
many minutes. For centuries,
even whole
mechanical
hours
clocks drifted
in a
wildly,
single day,
often losing
the pendulum
or gaining
changed
many
that.
minutes.
or even
With its steady
whole hours.
swings, errors
in a
dropped to
single
within
day.
about a minute.
The pendulum
And later,
changed
refinements brought this margin
With its
down
steady
to just
swing,
a handful of
errors
seconds.
dropped
to within about a minute.
For the first time,
And later, refinements
clocks weren't
brought
just
this
useful
margin
for ringing
down
bells,
to just a handful
but
of
reliable
seconds.
enough for science.
For the first time,
They could finally show
clocks
minutes
weren't just
and even
useful
seconds
for ringing
with
bells,
confidence, but reliable
Huygens
enough
built
for
on an
science.
idea first
They
noticed
could
by
finally
Galileo,
show minutes and
who had
even
observed
seconds
that
with
pendulums
confidence.
tend to swing at the same
Huygens
rhythm,
built on an
regardless
idea
of their
first
amplitude,
noticed by Galileo,
a property called
who had
isochronism,
observed
that pendulums tend to swing
But
at the
while
same
Galileo
rhythm
imagined a
regardless of their
timekeeping
amplitude.
device based on this
A property
principle,
called
he
isochronism.
never managed to construct one.
But while Galileo imagined
Huygens
that was the
was the
one
one who
device
made it
based on this
practical.
principle,
Using
he
pendulums
never managed to
regulate
regulate
one.
clock gears and
Huygens
give them
was
a
the one
natural,
who made it
dependable
practical.
rhythm.
Using
The
pendulums
breakthrough
to
was
regulate
immediate.
clock gears and give them a
Task-based
natural,
notions of
dependable
time,
rhythm,
once measured
The
roughly
breakthrough
by the
was
sun or
immediate.
bells, could now be
Task-based
broken
notions
into
of time,
short, once
fixed
measured
units.
roughly by the sun or
Astronomers
bells,
benefited
could
most.
now be broken into
With
short,
pendulum clocks,
fixed units.
they could track star
Astronomers
transits across the
benefited
sky
most
to within seconds.
with pendulum
Making
clocks,
careful
they could
observations
track
that
star
had been
transits
impossible
across
before.
the sky to within seconds.
Navigation too
making
began to
careful
change.
observations that had been
Though
impossible
pendulums
before.
couldn't function on moving
Navigation
ships,
too,
they set a
began
new
to
benchmark
change.
on land for
Though
how
pendulums
precise
couldn't
time might
function
guide
on moving
exploration.
ships.
They set
As the
a
pendulum
new
spread,
benchmark on land for how
clockmakers
precise
searched for
time
ways to
might
make it
guide
even more
exploration.
efficient.
In
As the pendulum
1671,
spread,
English clockmaker
searched
William
for
Clement
ways to make it even
developed
more
the anchor
efficient,
escapement. In
which allowed
1671,
pendulums to swing
English
in narrower
clockmaker
arcs.
William Clement
This
developed the
reduced
anchor
friction
escapement,
and energy loss, which allowed
keeping
pendulums
time
to
more
swing
steadily.
in narrower arcs.
By 1675,
This reduced
improvements
friction
led
and
to the
energy
deadbeat
loss,
escapement,
keeping time more steadily,
which further minimized recoil.
By 1675,
made the pendulum's
improvements
motion
led
smoother
to the
and more
deadbeat
regular.
escapement, which
These
further
refinements
minimized
moved
recoil
clocks
from
and made the
useful
pendulum's
tools
motions
into
smoother
truly
and
scientific
more regular.
instruments.
These
The effects
refinements
touched
moved
daily
clocks
life
from
as well,
useful tools into
In the
truly
1680s,
scientific instruments.
The tall, long case
The
clock,
effects touched
better
daily life
known
as well
as the grandfather clock.
In the 1680s,
the tall,
its
long
wooden
case
housing
clock, shielding the pendulum
better known
from
as the
drafts.
grandfather clock. With this
Emerged
protection, Its
Clocks
wooden
became
housing
more
shielding
consistent,
the pendulum from
and
drafts.
minute hands suddenly
With
mattered.
this protection,
Clocks
people
became
could
more
schedule
consistent,
meetings and measure
and
tasks
minute
down to the
hands
minute.
suddenly mattered.
Instead of the vague
People
span
could
of an
schedule
hour.
meetings and measure
In
tasks
workshops
down
and
to the
factories,
minute. Instead of
bells
the vague
synchronized
span
by
of an hour, pendulum clocks began
in
to
workshops and
regulate
factories,
shifts. Slowly
bells
reshaping
synchronized
how
by
work
pendulum
itself
clocks
was began to
organized.
regulate shifts.
The pendulum
Slowly
also entered the realm of
how
ideas.
work itself was organized.
Philosophers and
The
scientists
pendulum
saw
also
in its
entered
steady
the realm
rhythm
of
a
ideas.
model of the universe's
Philosophers
order.
and scientists saw
Isaac
in its
Newton
steady
drew on
rhythm
Huygens' work
a
in his
model
theories of
the
motion.
universe's order,
While thinkers like Leibniz
Isaac Newton
pointed
drew
to
on
pendulum
Huygens' work in his
isochronism
theories of motion
as proof of a
while
perfectly
thinkers like
regulated
Leibniz
creation.
pointed to pendulum isochronism,
The image of nature's
as proof
hidden rhythms,
of a perfectly
constant
regulated
and
creation.
measurable,
The
resonated
image of
deeply
nature's
in the
hidden
Enlightenment.
rhythms, constant
But
and measurable,
even the pendulum needed further
resonated
tweaks.
deeply in the Enlightenment.
Temperature shifts
But even the
expanded
pendulum
and
needed
contracted
further
metal
tweaks.
rods, throwing off timing.
Temperature shifts expanded
In
and contracted
1721,
metal rods.
George
Throwing
Graham
off timing.
introduced the mercury pendulum.
In 1721,
Using the rising
George
liquid
Graham
to offset
introduced
changes
the mercury
in length.
pendulum.
Using the
Later,
rising liquid,
John
to
Harrison
offset
improved
changes
on this
in
with the
length.
gridiron pendulum.
Later, John
Interweaving
Harrison
rods
improved
of
on
different
this with the
metals,
gridiron pendulum.
so their opposing expansions
Interweaving
kept
rods
the
of
pendulum's
different
length
metals,
constant, so their opposing expansions
By the
kept the
mid-18th
pendulum's
century,
length constant.
the best precision
By the
pendulum
mid-18th
clocks
century,
lost less than 1
the
second
best precision
per day.
pendulum clocks
An improvement
lost
by
less
a
than
factor
1
of
second
1,000
per day
over
An
pre-pendulum
improvement by a
designs.
factor of 1,000
Despite such
over
accuracy,
pre-pendulum designs.
pendulums had their limits.
Despite such accuracy,
They required steady
pendulums
ground,
had their limits.
regular winding,
They
and
required
careful
steady
maintenance.
ground, regular
crucially,
winding,
and
they
careful
failed
maintenance.
completely aboard moving
And
ships.
crucially,
They
where the
failed
roll
completely
of the sea
aboard
broke
moving
their steady
ships.
beat.
Where the roll
This
of the
exposed
sea
a
broke
major
their
gap.
steady beat. While pendulum
This
clocks
exposed
could
a major
regulate
gap.
life on land,
While
with
pendulum
remarkable
clocks
precision,
could regulate life on
sailors
land with
still lacked a
remarkable
way to
precision.
measure time reliably.
Sailors
at sea.
still lacked a way to measure
That
time
difference
reliably
between
at
land
sea.
and ocean would soon
That
become a
difference
matter
between
of life
land
and death.
and ocean
would soon become a matter of life and death. The loss of 4 British warships on October 22, 1707, was a turning point in navigation. When they struck the Isles of Scilly, nearly 1,400 sailors drowned. The cause wasn't storms or enemy fire, it was miscalculation. The fleet's navigators could not determine their longitude. They had missed their true position by 50 miles, a fatal error. Longitude, the measure of how far east or west a ship had travelled, required precise time. Without a dependable clock at sea, mistakes were inevitable. Longitude depended on comparing 2 times, local noon, when the sun was at its highest point, and a fixed reference time, typically Greenwich. Each hour of difference equaled 15 degrees of longitude. On land, pendulum clocks handled this with newfound precision. But on the rolling decks of ships, pendulums failed completely. Their swings collapsed under constant motion, leaving sailors to rely on dead reckoning, estimating position by speed and course. As the Scilly disaster proved, guesswork could be deadly. In 1714, Britain's Parliament offered a prize of £20,000. Today, about $4 million, through the Longitude Act, to anyone who solved the problem. Into this challenge stepped John Harrison, a Yorkshire carpenter turned clockmaker. With little formal training, he spent decades obsessed with the idea of a sea clock that would keep true time under harsh conditions. Between 1730 and 1760, he built 4 major designs, each learning from the last. His first, the H1, tested to Lisbon in 1736, used counterbalanced beams in place of pendulums to survive rough seas. It impressed observers, but Harrison pressed on, knowing it wasn't enough. His H2 and H3 prototypes introduced ingenious new escapements and temperature compensation, but they were too large and impractical for regular use. The breakthrough arrived with H4 in 1761. No longer a bulky experiment, it resembled a large pocket watch. Its key innovations were a balance wheel regulated by a spiral spring, a grasshopper escapement built to reduce friction, and a bimetallic strip to cancel out the effects of temperature changes. Taken on the 1761-62 sea trial to Jamaica, H4 stunned the observers. After 81 days, it had lost only 5 seconds, accurate enough to locate a ship's position within about 10 miles after weeks at sea. It was, by all measures, the solution Britain had been searching for. Yet Harrison's fight wasn't over. The Board of Longitude, wary of granting the prize too easily, doubted the results. They demanded more trials and even copies of the design, dragging the process into years of delay. His son William carried H4 on another voyage in 1764 to Barbados, where it performed just as brilliantly, losing less than 39 seconds across 5 months. Even with repeated proof, the board withheld the full prize. It took the intervention of King George III in 1773, who personally tested H4 and demanded the injustice end, for Harrison to finally receive a partial payment of 8,750s after nearly 40 years of effort. Once accepted, the marine chronometer changed navigation overnight. Captain James Cook carried a copy of H4, known as K1, on his second voyage, charting the Pacific with accuracy no sailor had known before. Soon, navies across Europe adopted chronometers as standard. By 1825, Britain's Royal Navy alone had more than 800 in service. Merchant ships followed, and by mid-century most long voyages relied on them. Wrecks decreased, routes shortened, and insurance rates fell. What had once been a life-or-death guessing game became a science. Harrison's work inspired global refinements. French, Swiss, and later British watchmakers improved the balance wheels, escapements, and lubrication. By the late 19th century, a standard naval chronometer lost less than 2 seconds a day. These devices remained essential up to the 20th century, with even the Titanic carrying several on board. Beyond safe navigation, they spread standardized time. Chronometers carried Greenwich Mean Time across the oceans, influencing weather logging, scientific expeditions, and the eventual adoption of global time zones. Though GPS has long replaced chronometers, their legacy is everywhere. They proved portable precision timekeeping was possible, and in doing so, set the stage for modern science, exploration, and communication. From ships at sea to observatories on land, Harrison's clock stitched the world together in time. But precision did not stop with gears and springs. Inventors now began to ask a new question. What if a clock could run not on weights or wheels, but on electric force? By the early 1800s, inventors were beginning to think about time differently, not as something driven by heavy weights or wound-up springs, but as something that could be powered and regulated by electricity. This shift from gravity-driven systems to electric impulses opened entirely new possibilities. Instead of relying on winding and gears alone, clocks could now be maintained and even synchronized across distances with unseen signals. One of the first to attempt this was Francis Ronalds in 1815. He built an electrostatic pendulum clock energized by charges from a friction machine. The pendulum swung between electrified metal plates, receiving pushes each time it passed. His designs weren't practical. Constant recharging meant they couldn't run unattended. But he succeeded in proving that electricity could keep a pendulum moving with steady rhythm. Ronald sketched more than 30 variations, showing how deeply he wrestled with the idea. A far more influential design appeared in 1840 from Scottish inventor Alexander Bain. His electromagnetic clock used battery-powered pulses to drive and sustain the pendulum. removing the need for weights or wound springs. For the first time, multiple clocks could be linked together to share the same signal, creating synchronized master and slave systems. Factories and railway stations quickly saw the appeal. Imagine your entire city set to one master clock. Suddenly, precision wasn't confined to a single tower, but could ripple across whole networks of timekeepers. Some of Bain's versions even recorded time by printing marks onto paper tape, an early step toward time logging. Early electric clocks, however, met with plenty of resistance. Many craftsmen distrusted batteries that could leak, corrode, or die suddenly. Electromagnets were sensitive to changes in temperature, shifting the period of the pendulum slightly. But the benefits outweighed the drawbacks. Unlike traditional clocks that froze during winding, electric clocks ran without interruption. Factories and train stations began installing them as reliable, all-day regulators, while households slowly adopted simpler plug-in versions once electricity became widespread in the late 19th century. The next chapter opened with quartz. In 1927, Warren Marrison at Bell Labs created the first quartz clock, using crystals that vibrated at stable high frequencies when powered by electricity. His prototypes, bulky lab machines, were far more accurate than pendulum regulators, slipping by less than a second across months or even years. World War II accelerated their development. Quartz timers were vital for radar and communications, and by the 1960s, compact refinements brought them into homes and wrists, culminating in the Seiko Astron wristwatch of 1969. Suddenly, precision timekeeping was no longer limited to observatories or navies. Anyone could buy it. Quartz fundamentally changed expectations. A cheap bedside clock could outperform intricate, centuries-old mechanical chronometers. Sports adopted quartz stopwatches to measure hundredths of seconds. Factories linked networks of synchronized displays to a single quartz controller. Even national observatories turned briefly to quartz regulation before something even more stable came along. Of course, electrical clocks had quirks of their own. In some regions, electric wall clocks synchronized with the 60 Hz frequency of the power grid, which worked as long as the grid itself stayed consistent. Early quartz watches drained batteries more quickly than promised. Electromagnetic designs often produced faint humming sounds. Yet these flaws never outweighed their reliability. By the 1970s, quartz timekeeping dominated so completely that mechanical watchmakers faced a crisis, with once prized brands pushed aside by mass-produced quartz watches from Japan and beyond. Just as important as their accuracy was their form. Freed from pendulums and large winding mechanisms, electric clocks could adopt entirely new looks. In mid-century kitchens, brightly colored sunbeam clocks became everyday appliances. Designers like George Nelson turned wall clocks into modern art. And when digital displays finally matured, electricity carried time straight to glowing numbers. By the end of the 20th century, almost every computer and home appliance hid a quartz oscillator inside, quietly pulsing millions of times a second. Reliable, affordable, and nearly invisible, electric time had become the global standard. But precision seekers still pushed further. Quartz could hold time to remarkable degrees, yet it still drifted by small amounts. Meeting the new demands of science, navigation, and global networks called for something even steadier. Timekeepers based not on crystals, but on the fundamental vibrations of atoms themselves measure time when even Earth's rotation isn't steady enough. The answer arrived in the mid-20th century with atomic clocks, the devices that became the modern baseline for precision. Unlike pendulums or quartz,
These clocks rely on the unchanging rhythm of atoms themselves, making them the most stable timekeepers ever built. At the heart of this breakthrough sits the cesium-133 atom. When cesium is exposed to the right microwave frequency, every atom vibrates exactly 9,192,631,770 times per second. That remarkable consistency made it the perfect standard. In 1955, physicist Louis Essen built the first practical cesium atomic clock at the National Physical Laboratory in England. Its performance was astonishing. If it kept running for centuries, it would drift by less than a single second. This was more than an improvement. It was a complete redefinition of time itself. In 1967, the International System of Units officially adopted the cesium standard, defining 1 second as 9,992,631,770 microwave cycles of cesium-133. Before then, a second had been tied to Earth's rotation, 186,400 of a day. But astronomers already knew the planet wobbled and slowed in ways too irregular for modern demands. By rooting timekeeping in atomic vibrations, humanity stepped into a new era where physics, not the heavens, set the measure of time. That shift reshaped everything from global science to daily life. Cesium clocks formed the backbone of Coordinated Universal Time, or UTC, the standard against which the entire planet synchronizes. Institutions like the US Naval Observatory and time labs worldwide continually compare their atomic clocks through satellite links. At France's Bureau International des Poids et Mesures, these measurements are fused into a single, official timescale that keeps computers, financial markets, and communication systems aligned to within billionths of a second. Yet Earth itself reminded us it wasn't so easy to ignore. When scientists compared atomic time against astronomical observations, they found the planet's rotation drifted unpredictably, slowed by tides, shifted by earthquakes, and nudged by molten movements in the core. To reconcile atomic uniformity with the natural day, the world began inserting leap seconds into UTC. Since 1972, 27 leap seconds have been added, tiny adjustments that show just how sensitive atomic timekeeping has become. If this seems abstract, consider the GPS system in your phone. Every satellite in orbit carries synchronized atomic clocks. By timing how long radio signals take to reach your device, GPS calculates location within meters. A tiny error in atomic timing, just billionths of a second, could mean hundreds of meters of error on the ground. Without atomic clocks, navigation, telecommunications, and even banking systems would fall into chaos. And atomic timekeeping is still advancing. While cesium has anchored definitions for decades, new designs known as optical lattice clocks are pushing limits even further. These use atoms like strontium or ytterbium, trapped in grids of laser light, vibrating at visible light frequencies hundreds of thousands of times faster than microwaves. Experimental models already promise accuracy so extreme they would only lose a second over the span of 15 billion years, longer than the universe's current age. They're so precise they can detect tiny changes in gravity by simply moving the clock up or down a staircase, registering time itself stretching with altitude. Through all this, most of us never see an atomic clock. We encounter them indirectly, in a smartphone that syncs its time, in an ATM that logs a transaction to the exact microsecond, in streaming services that deliver music and video without skipping. Precision that was once reserved for observatories and navies now hides in everyday life.
And while atomic standards shaped the hidden networks around us, another story was unfolding. Timekeeping was no longer confined to observatories, towers, or laboratories. It was becoming personal, shrinking down from grand machines to something you could strap to your wrist. For centuries, precise timepieces belonged only to the few. Churches struck the hours, governments kept official clocks, and wealthy families displayed ornate pocket watches as symbols of status. Most people managed with sundials, bells, or nothing at all. That began to change in the 1850s, when watchmakers in Massachusetts adapted textile mill methods to timekeeping. The Waltham Watch Company pioneered the American system of watch manufacturing, using machines to mass-produce interchangeable parts. Instead of relying on artisans to finish each piece by hand, production could scale, prices fell, and ordinary people could finally afford personal watches. A tool once worth 6 months' wages now cost no more than a week's pay. By the 1880s, Waltham turned out hundreds of thousands of watches annually, putting timekeeping into the hands of middle-class workers, farmers, and railroad conductors. The spread of accessible watches subtly shifted expectations. Before, punctuality was a courtesy among elites. Now it became a daily standard. Farmers with access to up-to-date crop prices made better decisions. Factory workers timed shifts against a watch instead of the rising sun. And railroads ran ever more tightly synchronized schedules. In effect, watch ownership shifted punctuality from elite courtesy to daily expectation. The wristwatch had a different journey. In the late 1800s, wealthy women wore jeweled wristlets mostly as fashion. Men dismissed them as decorative, sticking firmly to pocket watches. That shifted only under the practical demands of war. During World War I, pulling a pocket watch out in the trenches was inefficient and dangerous. Soldiers instead strapped rugged wristwatches directly to their arms, with protective grills and luminous dials to make them usable in dim conditions. After the war, the association with soldiers and officers gave wristwatches new credibility, and returning veterans kept wearing them. Within a generation, the wristwatch became not just acceptable for men, but standard. By this point, the socio-cultural impact was impossible to ignore. Being on time was now measurable in minutes, not rough estimates. Factories tightened production with whistles and punch clocks. Schools rang bells tied to synchronized class periods. Employers often expected their workers to own reliable watches, and responsibility itself became linked to the ability to track time accurately. Even the technology of watches kept improving. In the 1920s, self-winding mechanisms allowed wearers to keep their watches powered simply by moving. Shock-resistant cases made them more durable, while waterproof housings expanded their use in outdoor work and sporting life. By the mid-20th century, military contracts had ensured wristwatches were not only common but necessary, from pilots measuring flight paths to sailors timing naval operations. Another major leap came in 1969, when Seiko introduced the Astron, the first quartz wristwatch. Its crystal oscillator ticked thousands of times per second with extraordinary precision, outperforming even the best mechanical watches at a fraction of the cost. Within a few decades, quartz dominated the global market. Suddenly, students, office workers, and commuters could carry laboratory-grade timekeeping on their wrists. Digital displays soon followed, with features like alarms, backlights, and stopwatches transforming watches into multifunctional tools, not just time indicators. At the same time, watches took on personal and cultural meaning. Children often received their first watch as a rite of passage.
Professionals chose models that projected identity: slim dress watches for business, divers' watches for sportsmen, and ornate Swiss mechanicals for collectors. Even as smartphones now tell time for many, wristwatches remain powerful symbols, whether as simple everyday tools, luxury heirlooms, or modern smartwatches that blend timekeeping with health tracking and digital alerts. But as individuals carried their own precise timepieces, a practical issue emerged. Without a shared standard, one person's noon could be minutes different from another's. Expanding railroads, telegraphs, and cities needed more than millions of watches. They needed a way to make sure everyone's time agreed. What if the clock in your town stood 12 minutes ahead of the one in the next city over? Before the late 1800s, that was daily life. Each community set time locally, using solar noon, the exact moment the sun reached its highest point overhead. New York struck noon while Boston lagged behind, and Philadelphia still behind that. It worked fine in an age of horse-drawn travel, but as trains and telegraphs shrank distances, the patchwork of times caused confusion and danger. Railroads felt the problem most. By the 1870s, the Pennsylvania Railroad alone dealt with over 50 different local times along its routes. Conductors sometimes carried multiple pocket watches, each set to a different town's time. Scheduling mistakes meant missed connections, and worse, even collisions on single-track lines when trains weren't running to the same clock. The problem grew urgent enough that the railroads themselves took action before government stepped in. On November 18, 1883, later called the Day of Two Noons, American railroads introduced 4 shared time zones: Eastern, Central, Mountain, and Pacific. Across the country, towns adjusted their clocks by minutes or even half an hour to match the new system. Chicago shifted its official clock back 9 minutes and 32 seconds. Detroit resisted longest, clinging to local solar time for decades before eventually giving in. Overnight, the patchwork began to vanish, replaced by a map where time snapped neatly into zones. Not everyone welcomed the change. Churches complained that standard time disrupted prayer schedules, and farmers disliked the difference between real noon and the official one. But the safety, efficiency, and simplicity of one shared system outweighed the objections. Within a year, most major American cities had fully adopted the new standard, and Canadian rail networks soon followed. International agreement came just a year later. In 1884, delegates from 25 nations gathered in Washington, D.C. for the International Meridian Conference. Several countries wanted their own observatories as the center of global time. France pushed for Paris, Britain for Greenwich. Ultimately, Greenwich won. One major reason was practical. Most of the world's nautical charts and shipping routes already relied on it, making Greenwich a natural choice as the 0 point. From that, the conference proposed dividing the world into 24 time zones of 15 degrees longitude each, matching the Earth's rotation. Adoption took years. France resisted Greenwich until 1911, while Russia only reformed its complicated system in 1919. China still keeps a single official time zone today, even though geographically it spans 5. Local adaptations added quirks too. Newfoundland, for example, chose a half-hour offset that persists to this day. On other borders, like Afghanistan and China, the step between clocks is as much as 3.5 hours. Even stranger, the international dateline zigzags to suit island nations, creating scenarios where travelers can literally skip or repeat a calendar day, depending on the direction they fly. For ordinary people, though, the most noticeable change was psychological.
For the first time, noon no longer meant the sun sitting overhead. It became a human construct, set by international agreement and transmitted over telegraph lines. Communities adjusted work, prayer, and routines to match clock noon instead of solar noon. The disconnection between what the heavens showed and what the clock displayed was subtle but profound. Yet standard zones made modern coordination possible. Railroads cut accidents drastically. Telegraph operators synchronized clocks across vast distances, allowing banks, factories, and newspapers to work in step. Weather services began timestamping reports, helping improve storm tracking. Astronomers, freed from the variations of local time, could compare notes across continents. The shared frame of reference created by time zones became the silent backbone of the global economy. This system solved one of the biggest coordination problems humanity faced, but it also revealed a deeper truth. Even as the world agreed on clock time, the sky above us still kept its own schedule. Solar noon often arrived far from official noon, leaving a small but noticeable gap between celestial time and the time our watches showed. That gap between nature's rhythm and human-made standards never really went away. Why doesn't a sundial ever quite line up with a wristwatch? The reason lies in the clash between solar time, the sun's actual position in the sky, and clock time, which follows a steady, mechanical rhythm. The difference can stretch up to about 15 minutes, depending on the season. This isn't because sundials are unreliable, but because the Earth doesn't rotate in neat perfection. The core of the mismatch, known as the equation of time, comes down to two factors. Our planet travels around the sun in an elliptical orbit, and its axis is tilted. These quirks mean the length of a solar day shifts slightly throughout the year. Sometimes the sun appears fast, sometimes slow, drifting just enough to put sundials and watches out of agreement. That's why some sundials include special curves engraved along their faces, helpful guides that explain why noon on your phone doesn't always match the moment the sun sits directly overhead. For centuries, this irregularity shaped how people organized daily life. Ancient Babylonian astronomers left tablets noting that the sun did not rise and set in perfectly even intervals. Later, medieval monks built their prayer schedules around shifting day lengths, compensating as sunlight stretched or contracted with the seasons. Cathedral sundials across Europe often had dozens or even hundreds of tiny notches scratched into their surfaces. Corrections added so worshippers could keep rituals aligned with both the sky and the clock tower nearby. The eventual solution was to average the difference. By the 19th century, timekeepers defined mean solar time, the average length of a solar day across the entire year. This smoothed out nature's irregularities into something clocks could follow consistently. Greenwich Mean Time, established in 1884, embodied this approach. Later, Coordinated Universal Time, or UTC, went even further, anchoring seconds not to the sky at all, but to the vibration of cesium atoms. From that point on, astronomy bent to physics rather than the other way around. Still, solar time has never disappeared. It persists alongside atomic time in subtle but persistent ways. Farmers often work by daylight regardless of what the clock says. Muslim communities set prayer times by the sun's position rather than the hands on a dial. Airlines still plan calculations for fuel and flight paths with solar cycles in mind, even if departure boards follow clock time. And every human body, guided by circadian rhythm, feels the same truth. It is morning when the sunlight tells us it is, not when an alarm rings. Modern technology reflects this uneasy balance. GPS satellites rely on split-second atomic measurements, but also include adjustments for the Earth's changing rotation. Solar power plants operate by the true position of the sun, not UTC. Architects design buildings to capture light more efficiently in summer or to shield it in winter. Calculations base it squarely on solar angles. Even our leap seconds, added since 1972 to reconcile atomic time with the shifting length of the day, serve as small reminders that nature refuses to follow a perfect schedule. This tension creates a quiet duality in daily life. Clocks give us stability, while the natural world continues its seasonal variability. Noon might mean different things depending on whether you're looking at your calendar app or at a beam of sunlight creeping across the floor. We live inside both systems at once, switching between them depending on context, planning meetings by the clock, feeling tired or alert by the sun. That ongoing negotiation is what makes time such a powerful force in human history. It has never been about clocks alone. From fieldwork to sacred rituals, trade routes to global communications, humans have kept measuring and restructuring time because shared order is the only way communities can function. And as each new layer of timekeeping built on the last, it wasn't just minutes and hours being shaped, it was civilization itself. Why does timekeeping matter beyond machines and measurements? Because every society has needed it as the foundation of collective order. From temples staging rituals to railroads guiding trains, timekeeping has never just been about knowing the hour. It has been a social contract that holds people together. Take the Egyptians. Their shadow clocks weren't personal trinkets, but instruments that set the rhythm of entire communities. Farmers relied on them to time irrigation. Pyramid builders organized labor around shifts, and priests linked ceremonies across cities to the turning of water clocks. Accuracy mattered less than coordination. Missing the right moment for the Nile's flood meant disaster. Time was, quite literally, survival. Later, the Benedictine monasteries of medieval Europe used the clock to mold daily life in ways both strict and enduring. Their schedules of prayer, known as the horarium, divided each day into fixed periods, with bells marking when monks should wake, eat, work, and worship. It was one of the first environments where daily routines were ruled not by sunlight, but by mechanical time. In many ways, it resembled the punch clock centuries before factories adopted the same discipline. The Industrial Revolution pushed this idea into wider society. In textile mills and workshops, whistles replaced the pealing of bells, summoning workers to shifts that no longer matched the natural day. Time became quantifiable in smaller units, and lateness, even by a few minutes, could bring fines. Workers had to adjust to machines that never stopped, which meant syncing human effort directly to clock time. Precision here wasn't abstract, it decided livelihoods. At sea, another form of standardization saved lives. John Harrison's marine chronometer in the 18th century gave sailors a way to calculate longitude with accuracy, ending centuries of deadly guesswork. For the first time, global trade and exploration could unfold with predictable safety, because shared, reliable time meant ships could know exactly where they stood on open oceans. It transformed navigation from hazardous art into disciplined science. And then came the railroads, where timetables showed the cultural impact in its starkest form. Conductors weren't just carrying passengers, they were enforcing synchronization. A missed departure time could derail not only one train, but entire networks of travel. When the Day of Two Noons arrived in 1883, and railroads adopted time zones across America, entire cities adjusted their clocks to align with the iron rails. Detroit resisted for years, holding on to local solar time, but eventually gave way, as did every other town. This wasn't just technical fine-tuning. It was a clash between local identity and industrial necessity. Cultures, of course, shape time in ways unique to their values. Islamic societies retained lunar months for faith, while using solar calendars for farming. The Chinese linked celestial events to imperial will, with eclipses treated as cosmic verdicts. The Maya sustained overlapping cycles, weaving sacred time with agricultural calculation in patterns far more complex than a simple clock face. Each system shows that timekeeping wasn't only practical, it reflected how societies understood their place in the universe. The pace has only quickened in the modern age. A stock exchange now values a few millionths of a second as fortunes shift with each digital trade. GPS functions only because satellites above Earth synchronize their time down to billionths of a second, compensating even for relativity. The same forces that once rang church bells now govern self-driving cars and the routing of planes across continents. Yet beneath this astonishing precision lies the same tension as in ages past. Our need to reconcile natural rhythms with imposed schedules. Farmers still rise with dawn, school calendars still echo harvest cycles, and our biology rebels when forced into clock patterns that clash with circadian rhythm. In offices, on factory floors, and in trading hubs, we continue to negotiate between the sun overhead and the seconds flashing on a digital screen. So the question lingers, what mattered most? Was it Benedictine monks rising to bells in the dark, factory workers driven by whistles, or sailors steering safely thanks to chronometers? Which timekeeping change do you think had the greatest effect on daily life? Church bells, factory whistles, or GPS satellites? Share your thoughts below. Because as history shows, each breakthrough in measuring hours was never just about marking time. It was about reshaping how people lived, worked, and even believed. And in tracing those patterns, we can begin to see how humanity's pursuit of order has always been written in hours, minutes, and seconds. From shadows on stone to the vibrations of atoms, the story of timekeeping is the story of how humans imposed order on daily life. Sundials divided the daylight, water clocks brought time indoors, and mechanical gears turned hours into shared schedules. Each leap didn't just improve accuracy, it reshaped how people worked, prayed, and traveled. The watch on your wrist carries those influences forward. Its design owes something to Egyptian shadow clocks, medieval towers, and Harrison's marine chronometers. It's more than a tool. It's a link to thousands of years of human problem solving. If you enjoyed this journey through clocks, like and subscribe for more overlooked history